Okay, I'm going to start the show. As a physics department, this is our first gig at a public lecture, so I have to say we're completely amazed at the turnout. It's fantastic. So let me welcome everybody. I'm David Kleinfeld. I'm a professor in the department. I welcome you. Dean Mark Thiemens of the physics division is here. He welcomes you. Dmitry Basov, our chair, welcomes you. And I guess the 45 of us in the physics department welcome you. And so modern physics today is really the study of matter and light in its different forms. Today's lecture by Brian Keating is sort of at one extreme. It's when matter was hot and squished, and it's really about the first couple of femtoseconds of the universe, where it was just this one compressed zoo of hot subatomic particles. Other people in our department study matter at more hospitable temperatures and densities. They just try to understand solids and all the very odd properties. Sometimes you get in solids where particles and currents will move motionless. Other people in the department are sort of at the extreme end and study things relevant to biology, where matter has begun to reproduce itself and even begun to understand itself, which is why we're all here in this room today. So let me introduce Brian. So Brian was born in Long Island, at Stony Brook, right? And where my sister went to college. And from there, he went to Case Western. From Case Western, he went to Brown to do his graduate work. And then he came back to California, started up at Stanford, worked his way south to Caltech, worked his way south to UCSD, and today he's going to talk about experiments he's doing in Chile, so he's keep going south. And I guess the next stop is the South Pole, right? And then that's the edge. Anyway, let's give a warm hand for Brian.
Okay, everybody, there's a lot of you here tonight, and only half of you are family members. So thanks very much, Mom and Dad, for coming. So today we're going to talk about the journeys that we take in astrophysics here at UCSD, the group composed of myself and my colleagues, some of whom are in the audience today. And I'm going to discuss this exciting quest that we're trying to solve, which is to understand the universe in its very first microseconds. Actually, we are even going farther back than that. Somebody recently asked me in an interview what we're looking for. We're trying to understand what happened in the first minute after the Big Bang. And I said, we already know what happened in the first minute, but we want to know what happened in the first billionth of a billionth of a billionth of a billionth of a second after the Big Bang. I said, why would you want to know that? What could possibly happen in that amount of time? So what I'm going to hopefully discuss tonight is the quest to understand the ultimate conditions that prevailed in the universe in that first instant. And we can only measure it today by way of these very sensitive telescopes that we build along with my colleagues and students and postdocs here. So I'm going to show a lot of pictures and give a couple of travelogues for the two experiments that I'm going to discuss today. One of which is shown on the screen here. And those of you in the first couple of rows, like they say at SeaWorld, you might get wet. You guys might get cold, because I'm going to show a lot of very cold, very, very distant places. So I was asked to give this lecture, and I was really excited to do it. I was told there'd be alumni here, and someone mentioned, well, maybe someone will actually want to donate money to UCSD. And I said, well, why don't they donate stock instead of donating? While it's actually still worth something, maybe we'll be doing them a favor too. Okay, so who are we? We are the UCSD Experimental Cosmology Group. And cosmology is actually really hard to do. We actually don't do any experiments. We don't change the temperature of the sun and ask what happens. We can't travel back to the beginning of time with a time machine, a physical time machine. I'm going to show you a type of time machine that we do use, and I'm really excited to see a lot of young people in the audience today too. And these are some of the young people and older people, all the way men and women, from the age of about 17 all the way up to 70-something. I won't ask their exact ages. But I want to point out the group that we have is about 17 astrophysicists, not astronomers or considered astrophysicists. We apply the laws of physics to problems in astronomy. And usually I'm asked, you know, you're an astrophysicist, you're an astronomer, I'm a Pisces, can you tell me something about the future? And I used to say, well, I'm not really that, I'm an astrophysicist, I don't do that, but I get it so often that now I just answer the question. So next week's going to be very unlucky for you. And yeah, so we don't study astrology, we study the beginning of the universe, which is the study of cosmology. And so this is the group of people that we do, that we have in my collaboration. In particular, I want to point out my closest colleague and friend, Dr. Hans Parr, professor of physics. He's actually, I guess he's the second in command in the physics department. He's a vice chairman of the physics department. And Hans and I have been working together for about 5 years, and I'm going to show some work that we've done together in Chile after I describe the experiment that we're conducting at the South Pole. So what do we study? We study the cosmic microwave background radiation, a lot of syllables. And what it means is we study the heat that's left over from the Big Bang. And the heat doesn't come in the form of energy that you can put your hand out and detect. Instead, it comes in the form of radio waves and microwaves, which is a portion of the electromagnetic spectrum that our eyes can't see. But if your eyes could see these wavelengths, you would see an image on the sky that looks like this. If you had exquisite vision, if you had tremendously sensitive vision, I'll explain why you need very sensitive vision in order to discern these images here. And we deploy these telescopes that we build, the technology that we build, from the very, very smallest quantum detectors that we can build with features that are 1,000 times smaller than a human hair. We use that to study the biggest things in the universe. We study the universe itself. We study the quantum fluctuations in the early universe that we believe led to the structure in the universe that we see today by imprinting this microwave background pattern with a special type of pattern called polarization. And I'll talk a little bit about that today. And we take these telescopes and we take them a long way from San Diego. We take them south, as David said. We take them not south of the border, not just south of the border, but we go into the southern hemisphere. And I'm going to display some images from the most recent deployment, the most recently deployed telescope called Polar Bear, which ironically is in the southern hemisphere. And then I'm also going to discuss first our experiment called BICEP, which is at the South Pole. So first I want to give a little preliminary. What we study is the very beginnings of the universe, and very little is known about those beginnings. As I said, we know what happened in the universe about a second after the Big Bang. We know the age of the universe exquisitely well. We know that the universe is 13.7 billion years old, with an uncertainty of 1 in that last digit. So that would be like me, I'm not going to look at anyone in particular, but looking at someone who's 137 years old and saying, I know your age exactly. I know it's between 138 and 136 years. So imagine how difficult that would be to determine. So we already know these properties of the universe exquisitely well, one of which is the age of the universe. But we're not satisfied. We want to go back earlier and earlier times, because a lot can happen in a nanosecond. In fact, most of the physical properties of the universe we believe were laid down in that first nanosecond. Okay, I sound like nano. But we believe that the entire conditions that we see today were determined then. And so after the universe emerged from this period of inflation, which will imprint the microwave background with polarization, after that occurred, then the dynamics of the universe were determined, or almost universally predictively determined. Not that we can determine that all 250 of us would be in the same place tonight as this room, but we can determine the aggregate statistical properties of the universe very accurately. And then after the timeline continues, after this period of inflation where quantum fluctuations prevailed, the microwave background pattern, which is shown here, was established. And that is a unique fingerprint, a tracer of the conditions that prevailed beforehand. And after that, the properties of the universe evolved. Very complex astrophysics, but the initial conditions are what matter to physicists like us. So what we want to determine is what happened in that initial instant. And so I want to make a detour to discuss the relationship between time and space. So many of us have heard of space-time. It sounds kind of exotic, but really it's the implication discovered by Einstein and others that time of an event and the distance of an event are related via the speed of light. So light travels at a finite speed. For many years it was thought to be infinite. I shoot this laser pointer at the screen, it gets there instantaneously. But actually that doesn't occur. Light travels at about in a billionth of a second. In 1 nanosecond it travels about this far, about a foot. And the implications of this are pretty astonishing. One is that if you look at someone close to you, if I look at these young men in the front row, I see them and they look young. And then if I look somewhere farther back, I see them when they looked even younger. So if you want to appear younger, you move to the back of the room. And that's because things that are farther away, light had to travel a longer distance, and it took a longer time. So therefore, for the light from the folks in the back row to reach me at the same time as these nice young gentlemen in the front row, that light had to leave earlier. And I'll illustrate that in just a second. And we speak of this by the fact that we describe a telescope as a time machine. Actually, your eyes are time machines, as I just said. But in particular, telescopes are time machines that allow you to see great distances and see back to very early times, and that's what's important to us. So I said that light travels about this far in a nanosecond, and that means that the moon, which is 250,000 miles away, 250,000 miles away, the moon takes, if I were to bounce a laser off the moon, as my colleague Tom Murphy does, it would take about 1.5 seconds to get from the Earth to the moon. And the sun, as many of the students in the audience could tell us, the sun is 400 times farther away than the moon, which makes it about 8.3 minutes away from the Earth by the speed of light as light travels. So time and space are connected, and here's just a diagram which says what I said in words. 93 million miles by the light travel time is 8.3 minutes, 8.3 light minutes. You've heard of light years. Light minute is just the analog for a shorter period of time, a little bit more friendly for us astronomers to deal with. And the moon similarly is a second and a half away from us. So consider this particular creature. Now my biophysics friends, David and others that are in the audience, will recognize this particular creature. This is the mayfly. And this is not a very seemingly well-designed organism for living. If you look at the description here from none other than Wikipedia, the lifespan is about 8 minutes of this creature. So it's got to cram a whole lifetime, college, graduation, but especially it has to reproduce. In fact, its mouth parts are vestigial. That means they're useless, and the digestive system is filled with air. So it's not going to eat very much in its first and its 8-minute lifetime. Okay, so consider this mayfly, and then put two of them, two twins, born at the same time. And one was born on the sun, not on the sun, it's not cooked barbecue mayfly, but one is placed in the sun, it's protected, it's born at the same time as one in the moon. So it takes 8.3 minutes for light to travel from the sun to the Earth. And the lifespan of the mayfly is only 8 minutes. So that means by the time you see this one alive, this one will be dead. And actually they'll both be dead, right? Because they both live only 8 minutes. They both have little clocks that tell them that they live for 8 minutes, but we don't find out about this one being dead until 8 minutes after it's actually died. Okay, now that may be a little bit morbid to consider, but at least these things are only born to die, really. That seems to be their only function. So the question naturally is, how far back can you look? If I keep looking back in this room, I eventually hit a wall, and I can't see any farther back than the wall, which might be 30, 40 feet away. So the question is, how far back can we look? And the answer turns out to be, we can look as far back as there was light. We can look through these objects here, these galaxies. This is the Hubble Ultra Deep Field image. Most of everything on this image is a galaxy, not a star. It looks like a star maybe at the resolution that you see, but only things that have these crosses, this one, and maybe a few others that you can see that have this cross diffraction pattern, those are the only stellar objects in this image. The rest are galaxies. Now, how big is this image on the sky? If you take a piece of paper and you put a dot on it, the size of a period, and you hold it at arm's length, that's how much of the sky this subtends. So think about all these galaxies crammed into this very small region of sky. And now look outside and imagine how many pieces of paper with little pinpricks on it would you have to use, those pinpricks, to tile the whole sky. An enormous number. There's an enormous number of galaxies. And each one has almost as many stars in it as the universe has galaxies. Hundreds of billions of stars in each one of these galaxies. But nevertheless, our telescopes can look right through them. They're transparent for microwaves. Microwaves go right through these objects, and we don't see them. We don't see the stars. We see very, very little effect from all these things in the way. So that means we're looking back. We're looking back in time. We keep looking back in time. This guy might be a little closer than this one, so our light would end here if we were using visible light. But now we're looking further back in time to this one. Maybe this one is several billion years old, maybe 10 or 15 billion years old. Or sorry, 10 billion years old. This one might be 13 billion years. And the Big Bang, we believe, occurred 13.7 billion years after the Big Bang. The Big Bang occurred 13.7 billion years ago, rather. So this is a little animation done by some friends of mine at NASA of what would happen if you zoomed into this plot, which is the CMB maps that we're endeavoring to make, and you zoomed into a region which looks to be cold. So that's a region which has an average density of matter which is larger. And you'll have to trust me on this. The matter density in that region is larger than the matter density in other regions. So it's an overdensity compared to the average 2.7 degree Kelvin microwave background radiation. That means there's more stuff there. that stuff being imprinted originally by these inflationary perturbations, then accreted by gravity. Gravity only sucks things in. As things suck in, they fuse, they form, hydrogen forms into stars, into helium. That emits light. The stars then formed into galaxies, these proto-galaxies. And then we see this image today when we look back using our telescopes. This is an animation of the WMAP experiment. I'll talk a little bit more about that later. And so we believe that that's how structure forms in the universe. That's how we get here. We see fluctuations in the microwave background produced by this mysterious inflation, this period of quantum fluctuations in the density of the universe at very, very early times. Those quantum perturbations then lead to an imprint of structure that we see today in the form of galaxies, stars, planets, people. So the Big Bang actually has a great deal of evidence that supports it. And here are 3 pieces of evidence, the last of which is what I study in detail. So the expansion of the universe implies that everything is expanding away from us when you go to a big enough scale. If you go out to galaxies that are far away from the Milky Way galaxy, you see every galaxy expanding away from you. Now that make you think that you're very special. Everything's moving away from me, or that you have bad breath or something. But that everything is receding away from you would seem to imply that the Earth is in a special location. But actually, we believe it's true for every galaxy in the universe that's not attracted to another galaxy. So that's the Hubble expansion, for which the Hubble telescope is named after Edwin Hubble. Edwin Hubble, I've seen a bunch of lawyers here tonight. I always have to poke fun at my lawyer friends who are here. Edwin Hubble is famous for saying his father really wanted him to be a lawyer, and he started law school in England, and then he came back to America, and the only thing he brought back was not a law degree, but he brought back a British affectation. And he said to his father, "Father, I'd rather be a second-rate astronomer than a first-rate lawyer." And so he actually ended up being much better than a second-rate astronomer. So another prediction of the Big Bang is the abundance of so-called light elements. I won't get into this. This is called nucleosynthesis. This is the prediction that the amount of matter that existed in the very early universe became the matter that we see today, complex matter. We're not made of hydrogen. We're made of carbon, nitrogen, etc. And those atoms were fused together in a very hot reaction and in very hot conditions that prevailed during the Big Bang. The next piece of evidence is the cosmic microwave background radiation, and that's the relic heat that's left over from the Big Bang. And like I said, in astronomy, we can't really do experiments. We can't turn up the temperature of the universe and ask what would happen. But what we can do is study the universe statistically, and that allows us to make predictions based on theoretical expectations and then go out and try to measure them. And another advantage that we have over experimental physicists like David and others is that we can, while we don't have the ability to change the control variables in our experiment, what we can do is go back in time with our time machines. And what we can observe are fossils left over from the Big Bang. And the CMB is a fossil relic in the form of light, heat, left over from the Big Bang. The abundance of light elements is a relic in the form of matter, the matter that we're made of, the sun's made of, etc. So there are relics that we can trace all the way back to the Big Bang. We all originated, all the material in our bodies originated in the Big Bang. And each one of these 3 tests, if it weren't astonishing enough on its own, is actually independent of the others. So it doesn't depend on the other 2 pieces of evidence. It's very solid scientific footing. So Hubble said the universe is expanding. As the universe expands, the wavelength of light shifts towards the red, and that's called redshift. So I'll talk a little bit about redshift today, and this is just meant to visualize what actually happens. The wavelength of light stretches as the universe expands. The universe isn't a ball. It's expanding, and we believe it's, in fact, flat. The space is flat, something we've learned from the microwave background as well. But the point to take away is that heat has cooled off since those extremely hot reactions that are required to produce the light elements. You need extremely high temperatures, nuclear reactor-type temperatures, millions of degrees Celsius, Fahrenheit, doesn't matter, very high temperatures to form those elements. And so the cosmic microwave background is a fossil left over in the form of radiation, light. Not nuclear radiation, light radiation. And Penzias and Wilson were 2 astrophysicists. Actually, looking back in 1965, they didn't have their astrophysics hat on. They were working for Bell Labs, where David used to work. And this was a lab that was quite astonishing. They led so many creations and so many inventions that we take for granted today, from the phone to the internet and other things. That's just astonishing. But one thing that they did do were they were involved in the first satellites that were launched by the US, the first communication satellites. And they found when they looked at these satellites, trying to get the data from them, trying to get signals, television or radio signals bounced off of these satellites, they found that they had an unavoidable amount of static that they could not get rid of. And that static didn't depend on where they were. To my knowledge, by the way, this is the only cosmology experiment that's ever been done from New Jersey. So that gives it a very big distinction. So they use this radio telescope here, and I'll show you this in an image. This telescope is in Homedale, New Jersey, northern New Jersey, not far from Manhattan. So one of the things they did is point the telescope at Manhattan to see if that's what's causing this hiss, this glow, this static on their telescope that they couldn't get rid of. When they looked at these satellites, they couldn't get rid of it. When they looked at the New York City, they couldn't get rid of it. When they looked 6 months later, they couldn't get rid of it. Finally, they concluded very courageously that this must be radiation left over from the Big Bang. And it was known to physicists at Princeton, including my PhD advisor, David Wilkinson, who the WMAP satellite is named after. It was known to them that there should be a temperature about this. They were racing to get to this, to discover this afterglow of the Big Bang. And they found out that these two Bell Labs scientists discovered it. They famously said, "Boys, we've been scooped." So, and not because this looks like a giant scoop. But this is a radio telescope that they use. It's a time machine. And actually, I can't use this. I used to, even as recently when I got to UCSD in 2004, I used to be able to say, when you turn on your television, about 1% of the static, when you change channels between channels, 1% of the static is coming from the origin of the universe. So, but now I can't do that because everyone either gets it on a computer or gets HDTV over cable. So nobody can possibly relate to, you guys can't relate to static on a television. What's that? But actually, 1% of these little grains of static come from the Big Bang. So that's pretty amazing to think about. So they won this very particular prize, the Nobel Prize, in 1978. And soon after that, it was thought that the microwave background, in order to produce structures, galaxies, stars, people, etc., had to have fluctuations in it. They saw it as completely uniform. It had a constant glow. Remember, even when they were pointing to New York City, they saw the same thing. And this, I should say, is a map of the sky cut like a globe, but laid flat, like you would lay flat a map of the Earth. So this is a map of the sky with the vision that they could see. They saw a uniform glow corresponding to a temperature of 2.7 degrees above absolute zero. And in 1992, there were actually fluctuations in the microwave background measured by the COBE satellite, which revealed, this is another globe type image, laid almost flat, which shows the fluctuations as measured by the WMAP satellite. So these fluctuations then, as we showed, we zoomed in on one of these spots that's blue, representing an overdensity, an overabundance of matter, representing more gravity that pulls on photons as they leave these gravitational wells. That causes a redshift or a cooling of the photons. And they won the Nobel Prize in 2006, John Mather and George Smoot. And on large scales, the CMB is so uniform that it's actually more uniform than a piece of glass. It's more uniform than a bowling ball. If you think of a bowling ball as the smoothness of a surface of a bowling ball compared to its radius, that's much, much larger than this, which is the fluctuations in the microwave background are 1 part in 100,000. So 1,000th of a percent of the overall value of 2.7 Kelvin. So this again is a zoom in on this particular pattern. And we'll see other images that we make. This is just to reinforce the fact that gravity is the most powerful force on large distances in the universe. On short distances, the most powerful forces are nuclear forces and electromagnetic forces. When the nuclear force becomes large enough, when the atoms become so close pulled together by gravity, they heat up and they fuse and they form these elements, which then form stars, which then form galaxies. So what we did is we wanted to measure this property called the polarization of the microwave background. And in 2003, I proposed to build a telescope which we would take down to the South Pole in order to measure these fluctuations of a particular sort that are indicative of the inflationary beginning of the universe, that are indicative of these quantum fluctuations, and in order to prove and to understand what happened in the very early universe. So I'm going to talk a little bit about this experiment. It works in the microwave regime of the electromagnetic spectrum. It's basically a refracting telescope, which means it just has lenses. It looks distorted here if you look over here. It just has lenses, and these lenses are cooled down almost to absolute zero as well. And it has detectors here, which look like little funnels, and that's really what they are. They're funnels that collect electromagnetic radiation. And then we have a refrigerator that cools us even colder than 4 Kelvin, down to 0.25 degrees above absolute zero. 0.25 Celsius, also known as 0.25 Kelvin. So this technology is enabled by these detectors that we developed with NASA. These detectors are built in fabrication facilities like the one we have at UCSD that my group uses now, called Nano 3 in the Cal IT Squared building. These detectors are about an inch across, and each one is sensitive to one type of polarization of the microwave background. This is almost as technical as I'm going to get tonight, don't worry. And then when we resolve the different energy into its either horizontal or vertical polarizations, we can then learn about the origin of the fluctuations that then imprint structure on the microwave background. Okay, so this is some pretty pictures. No, these aren't gold, completely made of gold. They're just gold plated, although I still watch people closely when they're in the lab, make sure they don't sneak one off in their pocket. This is what it looks like from the side. This is what a photon would see after traveling for 13.7 billion years. This would be the last thing it sees. And it would decide, well, I'm going to go into this pixel over here, this pixel over here, and this is cut off on the bottom, but it says 1/20,000th of a megapixel. So I've got my phone over here with a 5 megapixel camera. You know, it's the hottest new thing and everything. This is a very, very, very tiny fraction of a megapixel, 1 megapixel, let alone 5 or 10 or 20. But this has an advantage that this device doesn't have. I can cool this structure down to 3 Kelvin, 3 degrees above absolute zero, and it will work. That's where it's designed to work. I've tried to do that with my iPhone, and they won't take it back. Now, what are microwaves? Microwaves are the subject that we're trying to understand. So they're a portion of the electromagnetic spectrum, the most familiar of which is the visible light spectrum, which is just a tiny, tiny portion of the electromagnetic spectrum. And it's shown here in decreasing order of wavelength from the blue part of the spectrum to the red. And we study the microwave regime. And the question might be, this is another animation that one of my friends made. This is a simulation of what our galaxy would look like if you had vision in all different wavelength bands. So we just traveled into where this Earth is in our galaxy. It's in an outer spiral arm. And we're looking out from the Earth, and we're making a map of the sky. We're laying it flat like a globe. We take the globe, we cut it, we smooth it out as best we can. We make a projection of it. And then we look at the Milky Way. So with your eyes, you see this. In the infrared, you'd see that. In the far infrared, you'd see that. Finally, you get to the microwave, which is what we study, and you'd see a uniform glow until you remove the 2.7 degree microwave background's temperature that Penzias and Wilson discovered. Then you see these fluctuations, the origin of which we want to determine. And hopefully experiments like BICEP and Polar Bear will attempt to do this, will help us do this. So the question is, why do we use microwaves to do this? Well, microwaves are a portion of the electromagnetic spectrum where this temperature from the Big Bang, this heat left over relic from the Big Bang, that's where the portion of the electromagnetic spectrum that the heat left over from the Big Bang is in. Now, this has a very big implication for where we put our telescopes. We can't just put our telescope in San Diego, as nice as that would be. I wouldn't have to go away from home, although I'd still have to teach. And, well, no, I actually love teaching. So we'd obviously love to do it in a close, easy, convenient place. But San Diego, as we know, even though it has low humidity, has actually relatively high humidity compared to other locations on Earth. So the question that most concerns us is which type of environment is best suited for microwave astronomy, radio astronomy. And it turns out we want to go somewhere very dry. And the reason is, you know that you can't boil water with a flashlight. The energy that's required to boil water from a flashlight would require a tremendous amount of energy. Huge batteries, flashlight heating of a glass of water would be impossible. But you know it's very easy to heat up water using your microwave. And that's because water absorbs microwaves. So here's a water droplet in your microwave oven. So the microwave oven produces waves of microwave energy. They cause the atoms in the water molecule to oscillate, to vibrate. And when they do that, they interact with each other, essentially heating each other up via a force that's like friction. That causes them to heat up, and they absorb the microwave energy instead of letting it pass here from left to right, say. So now we built a telescope. That's the coldest telescope in the known universe. And this telescope is trying to detect microwave photons from the Big Bang. 13.7 billion-year-old photons. So we don't want them to get absorbed in water molecules in the Earth's atmosphere. So that would require us either to go to space, which is extremely expensive, although you could sell your Facebook stock if Mark Zuckerberg is here. We're taking donations. The microwaves get absorbed so efficiently by water vapor that we want to take it to an even better desert than in San Diego. And one of the two deserts that we use is the South Pole in Antarctica. So now begins the first portion of our discussion, which is a travel log. So Arctic comes from the Greek Arctikos, which means near the bear. And I don't know if anyone can guess what bear they're talking about. But when you say Antarctica, that's opposite of Arctica, which means that Arctic means the northern hemisphere Arctic region, and that must mean near a polar bear. So that's why I said it's ironic we put a polar bear in Chile in the southern hemisphere. But nevertheless, Arctic refers to regions of the globe where either the Arctic or the Antarctic, they happen to be locations which are potential candidates for placing telescopes. Unfortunately, there's no continent at the North Pole or in the Arctic. There's no continent there, it's just ice. So instead we go to Antarctica, which actually turns out to be much better. It's the coldest place on Earth. It's the biggest desert on Earth. And it's one of the two best places to build a telescope. So I'm going to talk about both of those places tonight. So here's an image of Antarctica, which is located here at the bottom of this globe. And here's the sun, just showing you why at different parts of the year, Antarctica is completely dark. 6 months of the year, the sun is completely below the horizon, including right now. The sun won't rise at the South Pole until September 23rd of this year. So where is Antarctica? It's at the bottom of your globe, so that's why you never see it. It's very hard to see. You have to lift up the globe and look underneath it. Here's a view of that. And the South Pole is located here. Here's New Zealand. So the way that we get here is we fly from California over here to New Zealand to this town here called McMurdo, which is a US base of about 1,000 people. And then we take another plane to the South Pole. And I'm going to show you this travelogue right now. Oh, here's a comparison between the United States and Antarctica. And I like this, I got this slide from these people, and it says Antarctica is the 5th largest continent. And to me that's like saying, I graduated in the top 80% of my class. You know, it's not so impressive. But actually it happens to be a particularly good place for astronomy because of two factors. One is extremely cold, and two is it's actually the highest continent by average elevation. The elevation of Antarctica, the average elevation, is almost 2 kilometers, so we're talking 6,000 feet or more. And most of it's covered with ice. So there's a huge ice cap on top of bedrock. There's no bedrock at the North Pole. So if you drill down at the North Pole, you come to the Arctic Ocean. You don't come to a continent. But if you drill down at the South Pole, you get to bedrock. That means you can build something and expect that it'll be there next year when you come back to see it again. So here's the weather. Here's a view from a webcam that the way that the South Pole looked in January when the sun was still up. The sun set on the first day of spring for us, which is the first day of fall in the southern hemisphere. There's a link that got cut off here. And then here's a picture of how it looked just a few weeks ago. There's actually an image here. It's too dark to see it. But they stopped taking images on tax day of all days. They stopped taking images on the 15th of April because there's nothing to see. So it's an excellent place for astronomy because it's a very dry and cold place. The water molecules freeze out of the atmosphere and precipitate out as ice crystals. It doesn't rain ever, and it doesn't snow very often. And despite these unfriendly natives that we witnessed down there, don't seem to be very hospitable, we still decided to come to the South Pole. So here's how we get to the South Pole. We start in California. Here we are in California. We have a port called Port Hueneme, which is near Oxnard, California. We build our whole telescope to fit. You notice here it says all materials must fit inside an LC-130, which is a ski-equipped military cargo plane. So everything has to fit in this thing, which is much smaller than a Boeing 737, and you'll see an image of it in just a bit. So that places severe restrictions, and it's one reason that it's not necessarily a clear-cut case which one is better, South Pole or Chile. Okay, so things go from here, they wrap around, they emerge over here in New Zealand, and then things go from New Zealand to McMurdo and then to the South Pole. We can ship stuff by boat, but eventually it still has to go in an airplane. The boats look like this, or the icebreaker that breaks through the ice so that we can get stuff there looks like this. And I would never want to be on this boat, but you can actually take a cruise, not to Antarctica itself, or not to this part of Antarctica, but you can go to the Antarctic Peninsula. So when you arrive in a beautiful place called Christchurch, New Zealand. And Christchurch looks like this, very blue, very Lord of the Rings looking. Beautiful city there. Had some earthquakes recently, but it's still in good shape. And then this is where the heroic polar explorers left from 100 years ago. We're in our 100th anniversary of the first scientific and expeditionary teams to go to the South Pole. It occurred this year and in December of 2011. And the British team was led by Robert Falcon Scott, kind of a cool middle name. And he left from Christchurch on 1910, and he stayed in the Antarctic until March of 1911 when he died. So he died after being the second person to reach the South Pole. And that must have been very, very depressing. That may have been one of the most depressing events in human history. And I'll show you some pictures of that that will illustrate what I just said. So this is actually carved by his wife. It's kind of poignant. His wife was a great sculptress, and she sculpted out of material in New Zealand. She made a sculpture of him, and actually he's facing north, so it's like as if he's coming home to be with her. So it's very romantic. But luckily today we have much safer ways of getting to Antarctica and back. And I'm going to show you those after I show you the only boat that I get on in this whole trip, which is the Avon River punts, little boats that go through the Avon River in Christchurch. So Christchurch I think of as a tropical version of England. If you've ever been to either Hawaii or England, imagine the two of them mixed together. So when you're there, the U.S. has a really tiny base where we pick up our clothing that we're going to need there because there's no Kmart's there. There's no place to pick up clothing while you're at the South Pole. So you need to bring all the clothing you're going to use with you. And believe it or not, we bring almost everything that's shown on the screen there. We bring many pairs of gloves, many pairs of boots. You can see people trying on boots. These are the boots that we use. These are vacuum or air bladder boots so you don't freeze your feet when you get to the South Pole. And we bring down multiple jackets, bibs, socks. Again, you have to put everything you're going to have for the next months, many months potentially, or years if you're going to spend a year there, which we do have people that have spent multiple years there, actually, that work in my experiment, with only a month or two off. They love it there. They have to bring, they get to bring an extra bag though. So that's kind of nice. They get to bring 3 bags of clothes. So you get a boarding pass. You go through a sign, and like kind of the sign that you go through when you go into New Zealand, what they're really concerned about you bringing in there are drugs. They don't want drugs at the South Pole. So it turns out you can bring as many grenades, weapons as you like, but there's dogs that sniff out for drugs because they don't want to turn it into some place of iniquity. So there's a fast way and a slow way to get there. There's a really slow way, which is take a boat, which I would never do. But the fastest way to get there is on a C-17 cargo plane. And you pick that up here in Christchurch. There's a big Air Force base there, essentially. And that's the fast way to get there. And here is the inside of a C-17, which is an amazing machine, except for the fact that there are essentially no bathrooms on this. No bathrooms and no windows on this plane. If you look around, there's almost no windows that you can see, and that's because cargo doesn't need to see anything. You know, an M1 tank doesn't need to look out the window. And they roll on these gigantic seats. They don't have tray tables. There are no stewards or stewardesses, no flight attendants that are here. And this is the fast way to get down there. This is the slow way to get down there. And believe it or not, this is a plane owned by the New Zealand Air Force. And believe it or not, it's about 1/10 of their entire Air Force. It's a C-130 that we gave to them from 1965. It's a 4-engine turboprop plane that's about half as fast as the jet, the C-17. So when you wake up in the morning at 5 a.m., go over to the airport, and you see this, you get a little depressed. Because the inside of this looks like this. When you sit knee to knee with people, and the bathroom on the plane is even worse than the bathroom on the C-17. It's affectionately called a honey pot. It's just a bucket. So we seem to have lost this display here. Okay, maybe we're back. Okay, there's also no in-flight entertainment on either one of these. You know, that's kind of what it looked like for a second there. You hang your bags of your clothing and your personal items up there, and there's 2 lines painted on the side of the plane, and those 2 lines painted on the side of the plane show you where the propellers are in the plane, and that's because sometimes those propeller blades can shatter and send a blade into the cabin, and has actually resulted in deaths before. Not in this particular plane, but I always choose not to sit there when I can. 6 hours later, depending on which plane you're on, you can start to see icebergs and evidence that you're in a place that's completely unlike San Diego, any place you've ever been before. I'd never seen an iceberg, and these may be about 40 or 50 feet tall. So it's really amazing to see this from, even from a high altitude plane. You land in McMurdo, which when I was there, the first time I was there, I've been there twice. The first time I was there was the warmest December, which is the middle of summer. I got there almost at the beginning of summer in 2005. And you see the runway here that you landed on. This is from the airplane. You see the runway here is wet, and that's because the ice is melting. It was so warm there that particular December that ice was melting. And when you ever step off on a plane, you know you're on an ice runway, and you step into about a half a foot of water, it's a little disconcerting. But later in the season, they move it farther away where it's colder and the ice is about 12 feet thick, so you don't have to worry. And this is Mount Erebus, which is an active volcano down there. So you see here evidence that Antarctica is a continent. That's bedrock. That's actual rock. It's actually lava, rather, not bedrock. And it's left over from volcanoes, which do at some point sit on bedrock, maybe way down here, that you can't even see. So Antarctica is a continent. There are rocks there. So unlike the North Pole or the Arctic. Here's your super shuttle. You catch us into town. And as you drive along the freeways, this is an enormous vehicle. Everything in Antarctica is exceptional, especially the people that work there. It's really quite amazing, the types of people that you get to meet there. And I'm going to give you guys some links to those of you young people that are interested, old people that are interested in possibly volunteering to work there. I'll give you a link at the end of the talk. So you drive down these freeways. Here's your freeway. There's no traffic jams. You drive into town. You arrive and you're confronted with going to the ATM because you need local currency in order to buy things there. And you may ask, well, what could you possibly buy there or do there? Well, there's a couple things you could do there. Here's a view from above. I call it a mixture of like UCSD campus and a strip mine. I like it. Some people don't like it, but it's very industrial, very rugged. But it's a site of a lot of history as well for the exploration of the Earth and the exploration of the universe. Here's a bowling alley that was built by the Brunswick Corporation, and this is the last remaining manual pin-setting bowling machine that's available in the whole world. So they're actually considering paying the Antarctic ruling agency, the NSF, that owns this bowling alley, paying them millions of dollars to ship it back to some bowling museum, which is I don't know where it is. Somebody probably knows where it is. Okay, so when you hit a strike, it's kind of a drag. You have to go down and set up your 10 pins. So strikes are discouraged. You can also go to one of two bars. There's two bars down there. This one, there's no smoking, unlike somebody seems to be smoking now, but there's no smoking allowed in this bar, and you see it's very orderly. People are clean, quiet. They're eating chips, drinking soda. Or you can go to the smoking bar, which looks like this. After a couple of drinks, there's a lot of liquor and smoking, and the sun is out, which makes it very incongruous to be somewhere that you might associate with a dance club, and the sun is blazing bright because all day long the sun is out during the summer. The next day you get on a flight to the South Pole. This is a ski-equipped C-130. These are gigantic skis. And the planes, instead of being called United 451, they call them Skier. So this plane takes off, they say, Skier 127, you're cleared for takeoff, and they take off down this enormous ice runway and fly about 2.5 hours to the South Pole. And a couple of times I've been in these planes and it was just me and my graduate student. So that's pretty impressive. So I thank you already. You guys have already donated a lot of money towards this project through your tax dollars that pay for these adventures that we get to take scientifically. But I should note that actually this is considered a very important military hardware. The U.S. doesn't sell these ski-equipped cargo planes to any other government because they're worried that they could be used against the U.S. in time of an attack. So we keep them ready. They train with us. It's usually the New York Air National Guard. And they'll let you go up into the cockpit, which is really fun for me as a pilot to go up and talk to these guys and see how everything's going. Except when you go up there, it's a little disconcerting. And the sun is so bright that they block it out with maps. And then they're reading a book because they've done this 6 times earlier in the day. They've already made this trip. So that's kind of fun to go up there and see them reading until you realize that they should be looking out the window. You land at the South Pole about 3 hours later, and the first time you see my experiment, the bicep experiment, is located here. And here's an aerial view of it from a plane, a photograph taken from a plane. This is the layout of the South Pole. We're divided into a section called the dark sector. Sounds like where Darth Vader lives, but it's really to mean that you can't use radios, you can't use cell phones anywhere down here anyway because you don't have any coverage. No one can hear you now. When you're down there, you can only get phone calls about 7 hours a day from the South Pole using a satellite radio link. And this is the layout, so that where you live is over here, where I work is over here, and this region you're not allowed to use anything that broadcasts electromagnetic energy. This is where you pick up your stuff. This is called the passenger terminal, International Passenger Terminal. You don't get your passport stamped here, unfortunately. But I want you to remember what this building looks like, because you're going to see a cousin of it later on. So this is so we got there in 2.5 hours from McMurdo, but it took several months for the explorers, for Amundsen and Scott, to get there. So this is what it would have been looking like when they got there. These are here they are. Here's their party. They look very, as I said, they're going to look very depressed when you see them. And they got to the South Pole They've been working their whole lives to do this, spending the equivalent of what would be hundreds of millions of dollars back then, carrying scientific supplies. They collected meteorites. They collected, maybe I'm stepping on something. They collected meteorites. They collected geological samples. And this whole trip was leading up to being the first people ever to get to the South Pole, like getting to the moon. They wanted to be first. What do they do? What did they see when they got there? They saw these guys had posted a tent. They had left a long time ago. They put up a tent and a Norwegian flag. So what did they do? They were actually very good scientists, and like other explorers, they got there and they said, well, maybe they didn't actually get to the exact South Pole. Maybe they were 10 feet off. Let's take some measurements. They did. They found out that they did a good job. They actually had discovered the actual geographic South Pole. But here's what it would have looked like. These structures, these snow waves, these are frozen waves of snow called sastrugi. And imagine skiing over these with no animals. The British didn't use animals. The Norwegians did. And then they ate them when they got to the South Pole and on the way back. So they brought horses or dogs. And the British couldn't bring in themselves to eat their dogs. So it probably cost them their lives. But PETA would be very proud of them. And you see these snow waves here. They had to ski over these waves for 700 miles with an elevation change of 10,000 feet at one point. So amazing accomplishment. It's really sad they died just about 100 years ago. So it's the centenary of that. There's Amundsen. Now today, so he said famously, Robert Scott said, "Great God, this is an awful place," because it really was very tragic in some ways for them. He probably knew he was going to die because he got there in January and he knew he only had about a month and a half to get home, and he knew that would be very unlikely to do that. But it turned out he only died about 10 miles away from his food supplies and a safe storage place for where he could have stayed and waited it out, a storm that caught them. So this is South Pole today. I say, great God, this is an awesome place because the station has amazing things in it, like a basketball court, a sauna, a greenhouse. Here's the newspaper that's published in Antarctica. It's no competition to the Union Tribune. It's published on the continent. They publish 1,000 copies a week. And here, if you can read it here, it says that this is not a chef at the South Pole, but a sous chef. So we not only have chefs, that's obvious, we have sous chefs. And this one is French trained. It's Michelle Gentil. She's preparing cheese enchiladas for lunch, and it shows you that she's worked for all these different celebrities, Liv Tyler and other people. So, so it's we're pretty fortunate. The food is excellent when you get there, when you have sous chefs that are so trained. Makes you wonder what the real chefs are like. This is what the rooms look like. They're like dorm rooms. If you stretch out your arms and your wingspan is wide enough, you can touch both walls. It's smaller than a California state prison cell, which is very interesting to know. Here's me. You just have this one window which you have to block out with because you won't be able to sleep at night with aluminum foil. It's always popular. Here's me inside one day, and you see the iconic South Pole Dome in the background, which is scheduled someday to be shipped back to Port Hueneme in Southern California. So we'll be able to go visit the dome. That'll be pretty exciting. So you unpack and you take your own hero shot. You did such heroic stuff by getting on a plane and letting some people fly you across the world. And then you start going to work. So walking to work looks like this. You go across the runway. You see some other experiments. This is a companion experiment of ours. You get to BICEP, which is located upstairs in this building over here. And remember I said that you'd see a building that looks a lot like the passenger terminal? Well, this is our outhouse. Okay? You see that there's nothing connecting the building. These are just support structures so the snow will blow through. There's no plumbing here. So if you want to go to the bathroom in minus 40-degree weather, you have to suit up, go outside, go into the outhouse. And again, remember what the South Pole passenger terminal looked like. And I'm just hoping that they got the order right, that they didn't use the outhouse to make the South Pole passenger terminal. So we built the experiment. This is us, the day that we got the experiment to work. And then soon after, word got out and we had some dignitaries arrive. So maybe some of you can recognize this as Senator John McCain. This is about a year and a half before he decided to run for president. So he's outside, and I'm hoping that he'll say, to detect inflation, we need more stimulus. So hopefully BICEP would get some stimulus. But it's very cold outside. This is about -30, -20 the day he visited. And so we brought all these representatives and congressmen and senators, et cetera, inside. And naturally, he's an elderly gentleman, so it's nice and cozy inside. And so he fell asleep. He wasn't particularly dazzled, I guess, by the experiment. But I think that he was dreaming during this event. And when he was dreaming, he believed that he would discover a polarizing running mate from somewhere very cold. Now, he happened to get the polarity wrong because he chose from Alaska, not the South Pole. But hopefully it was a very fruitful visit for him. This is a photograph of the green flash. You guys have heard of the green flash. They're green flash concerts that we have at Scripps Institute, at the Birch Aquarium, rather. So you can see the green flash down there for 3 days. The sun is just moving along the horizon. It's just kind of gracefully gliding around the horizon. And then it slowly sinks and gets lower and lower, and then finally it's gone. And right before it goes away, you see this green flash, but it lasts like it does here. It lasts for a couple of seconds, maybe. There it can last for up to 3 days. So it's quite astonishing. And this was taken by our winter rover. His name is cut off down there. So we pay somebody to spend the winter months there, called a winter rover, to take data for us so that the scientists don't have to spend their time there. We can come back, look at the data, analyze the data. And so they get paid very good salaries. They get paid, when we hire them, we say, look, we're going to pay you $70,000 a year, and you only have to work for 1 night. And that tricks a surprising number of them. So this is what the maps look like from the Big Bang. These are images of those fluctuations. These are the very deepest maps ever made of the universe. And we're working on testing these for the indication of these quantum fluctuations that occurred during the Big Bang. These are 2 different maps that compare to each other, both made by BICEP. They're both exceedingly deep. And by comparing the features between the 2, we can prove to ourselves that what we're really looking at are what I call the birth pangs of the Big Bang, the fluctuations that led to the creation of the universe. You go home on a C-130, C-17, which is very nice. And then you can spend the winter there, as I said. There's a couple links I can give you guys. The minimum salary is about $65,000 a year. There are jobs that you can get at various websites. You can look up South Pole winter rover. There's actually very serious competition for these jobs. And sometimes couples go down there. That would be very interesting. I don't know. Do you want to go, Sarah, to the south? No, she doesn't want to go. Okay, so we're moving north again. So polar bear is usually in the north, near the northern hemisphere. So we're moving north away from the South Pole. We get to Chile. And why do we want to build polar bear? I just told you BICEP is so nice. Well, BICEP is a small telescope. The whole telescope can be cooled to absolute zero almost. And we've been observing with it for several years. But on the other hand, it's such a small telescope. It's only 5 feet tall and about 1.5 feet wide, that it doesn't have the angular resolution that we need in order to detect exotic phenomena that we know exist in the universe, such as neutrinos, primordial magnetic fields, dark energy, and dark matter. And for this, polar bear can do this by measuring the properties of what's called gravitational lensing. Einstein showed that gravity acts like a lens. It distorts the trajectories of light. So as light moves from the Big Bang, from the CMB, when the CMB was formed, as it goes by matter, it gets deflected. And that deflection tells us not only about the original light, but also about the lens that's doing the deflection. And that's how we can learn about properties of the neutrino, for example. So only polar bear, only a big telescope like this is a polar bear, which is located in the Atacama Desert. This is the way it looked about a month and a half ago, 2 months ago. It's a big telescope. I'm going to give you some facts about it, some numbers on polar bear. It's located here in northern Chile, in the Atacama Desert, which is this region near Bolivia, Argentina, and Chile. And there's actually an active dispute zone. These countries have been at war for almost 100 years or maybe more. And so there's actually minefields from mines that are 100 years old, because Bolivia has no access to the ocean. So they've always been interested in getting it. And to get it, they would go through the Atacama Desert. So there's a big controversy about that. Anyway, it's a 3.5 meter telescope, which means 11.5 feet in diameter, enormous telescope. It has 1,274 detectors compared to BICEP, which has 100 detectors. So it's 12 times as many detectors, cooled to the same temperature at 17,000 feet. I think it is this cable over here. So it's the second highest observatory in the entire world. The highest observatory is only about 2,000 or 3,000 feet higher, and it's located right nearby. And this is our array. So this is closer to a millimegapixel, 1,000th of a megapixel. It's getting up there. So we're excited by the prospects of why polar bear would be good. So the question is, why wouldn't you go to the South Pole? I just told you the South Pole is great. Well, the South Pole is great, but I was led to go to Chile for a different reason. And that's this guy here. If you look at this guy's shirt, this is my son Isaac. So on the shirt here, I'm not very good with Spanish, but if you magnify this, it says I think it says dessert of desserts. So that would be very delicious to me. No, it actually says desert of deserts. And so it's meant to represent the fact that the Atacama Desert is the driest desert on Earth. And it's also the highest desert on Earth at 17,000 feet. So thanks to Isaac, we discovered this. So at 17,000 feet, life is pretty unusual. We're almost above half the atmosphere of the Earth. So here's a water bottle we take up and take down, and when we take it down, if we've had some water out of it, the water, the air inside is essentially under vacuum, under pressure, that compresses the bottle tremendously. So there's a couple of advantages to going to Chile versus the South Pole. And there's essentially a religious war between scientists, which is better, South Pole, Chile, South Pole, Chile. I have experiments in both places, so I can't make up my mind, but actually both have features that work in their favor. One of which at Chile is that we can get there overnight. It takes about a week or 2 weeks almost for me to get to the South Pole. And depending on weather, it can be essentially a month. But you can always get to this Chilean site pretty much within a night, an overnight flight, plus some driving to the site. You can also get deliveries there, and you can get gigantic equipment there. Remember I said all the pieces of equipment that went into BICEP had to fit in this small plane where the people's knees were touching each other. So here we can get down anything we want, because it all goes by cargo ship and then taken by boat. Here's a travelogue analog of getting to Chile that I did for getting to the South Pole. So the first stop is Santiago, which is in central Chile. Then you fly north. It's kind of frustrating. You fly 12 hours. Then you get back in a plane, go north for 2 hours. Why don't they let me off sooner, you think? You land in Calama Airport, which is just a very small airport in the middle of nowhere where these giant jets can fly into. Then you drive about 2 hours to San Pedro de Atacama, which is a really nice kind of adventure rustic town in Chile. And here's a street, what the streets look like in San Pedro. Very authentic Latin American, very nice to see for me when I went there. You see dogs everywhere. And in fact, there's a dog in almost every image here. Here's a dog over here. And groups of crowds and nice culture there, a lot of cafes, very nice place to visit. It's often called San Pedro de Atacama because of all the dogs. You find this one is in a shop. These will just sleep in the street in the middle of traffic. It's pretty funny. Here's a rush hour scene. There's a dog back there. This is where we stay. These are our dorms there, much nicer than the dorms at the South Pole, bigger than a prison cell. And they're basically like a little bed and breakfast that Hans and I and our students stay in whenever we're down there. And then you take a road that goes all the way up to 17,000 feet. And most of it is paved except for the last 3,000 or 4,000 feet, which is unpaved, which is pretty rugged. So this is driving up the mountain from 9,000 feet where San Pedro is, all the way up to 17,000 feet. Here's the paved part of the road going up. Sometimes it'll snow on the road. This is off-roading to get up to the site. Here, the last several miles and the last several thousand feet, you have to go in a 4x4 vehicle to get past the rugged terrain, and also there can be snow that you have to encounter as well. So it actually gets plowed, which is very nice, and then we drive all the way up to the telescope, and as I said, this is what polar bear looks like. So 11.5 feet across. I'll show you some more pictures of it in just a minute. Life at the site is very relaxing. It's also very hard work. You're up, you're breathing oxygen through a tank on your back most of the time. Here is a picture of us having lunch. At the site, some UCSD team members. We have these cargo containers, little shipping containers that we've made into laboratories that we oxygenate to make it a little bit easier to live in there. But most of the people carry oxygen and they breathe oxygen through cannulas in their noses. We had to turn this barren mountaintop into an observatory, and that was a huge, huge feat for us to do. But now that we've done it, it's really exceptional. It offers us a great opportunity to build more telescopes here, and to create to access more data than we would be able to access with say, BICEP. So that's a great opportunity, and here's how we did it. We graded the whole surface. We plowed the surface of rocks and made it uniformly level over a very wide space about the size of a football field. And then we brought up trucks of concrete, 6 trucks of concrete, and poured a pad of concrete for the telescope to sit on. Here's us pouring the concrete, or some engineers that we hired. And then the telescope came together in pieces, and here are some pieces. Stephanie Moyerman is a grad student, and there's Hans dressed up showing you how cold it was. The telescope is only about half completed here. We're installing these panels here. These panels aren't even on. And all the labor is done, manual labor, by our students, postdocs, professors. and a few engineers that we hired that are local Chileans. So they help us translate and speak the language. Sometimes the weather can be really tough up there, even at 17,000 feet. You can have blizzards, you can have snowstorms. It doesn't rain up there, but it can be very foggy. It can get shrouded in fog. But most of the time, it's very deep blue. If you look at the zenith here, this is only looking up about this high, about 20 degrees up. If you look at the zenith, it's almost like being in space. It's almost like looking at this deep, deep indigo azure color that is completely unexpected from those of us that live at sea level. So being at high altitude, as I said, we're over almost half the atmosphere of the Earth, half the oxygen, half the water vapor, more than half the water vapor. And we're able to see into space, almost like being a satellite. Not quite, but almost, at about 1% to 2% of the cost. We got first light when the telescope first started taking astronomical data, which you can see in the shot over here. Not very exciting. You're not going to say that please book my flight to Stockholm to get my Nobel Prize from this. But this is important data proving that the experiment is going to work. And I'll show you some maps that we've made. So when we actually take those strips of data, we assemble them and we make two-dimensional pictures that look like this. If we're looking at a planet, this is Jupiter we're looking at. And then we can do this and we turn our attention to looking at the microwave sky, looking at the microwave background radiation. And this is a map that we made with only 10 hours of data with our detector system, with Polar Bear. So this is extremely competitive. Here's WMAP, that satellite that was launched for $250 million. And it took 7 years to make these maps. We do it in 10 hours. Because our detectors are much more sensitive than what they could launch 10 years ago. They launched it actually more than 10 years ago. And it's been taking data for over 9 years by now. And here's the comparison what BICEP sees. So BICEP, it took a year to make this image. Again, we have 10 times fewer detectors in BICEP than we're able to have in Polar Bear. And BICEP and Polar Bear cost about the same. But detector technology is advanced. We're building much more sensitive detectors and making more of them. And this is how Polar Bear looks today. It's all put together. It's all dressed up. And we have a neighbor down there, which is actually the world's most expensive astronomical observatory. It's called ALMA, for the Atacama Large Millimeter Array. It's $1.5 billion. I guess Mark Zuckerberg could still pay for this. And the telescope is down here. It's made of these enormous 12-meter dishes, much bigger than Polar Bear. Here, two different types of them seen up at the site. This is at 16,000 feet. They're about 1,000 feet below us. And this telescope is about 40 feet across, enormous telescopes. They're not looking for the Big Bang. They're looking for properties of asteroids, stars, galaxies. They're not looking for cosmology the way that Polar Bear is. And then I thought I'd end with a couple images of things that you never see at the South Pole, but we get to see them in Chile. So one thing that we see, we get alerts for active volcanoes, which is kind of spooky when you're going down there. This volcano is Volcan Lascar, which is only about 30 miles away from where Polar Bear is. And you get a warning in your email, and it says, the authorities have put the whole area on warning due to increased activity. There's going to be sound, explosions, ash in the air, and then evacuation details are being put into place. That's always scary to see that. And then I thought, ominously, it says, we will inform you when the conditions get worse. That was pretty scary. But actually, nothing happened. This was back in January when I got there earlier this year. Another thing you don't see are animals, any animals. Nothing lives at the South Pole besides people. It's actually forbidden to bring any animals to Antarctica under international treaty. There are two things that are forbidden, animals and styrofoam, which I find pretty interesting. So here's a llama. This is a giant llama. They seem to be pretty friendly, although I wouldn't get up too close to it. Here's a big falcon that you see just waiting for a weary passerby to run out of water and then start having its lunch. Here's a beautiful pink flamingo near an oasis, which we travel to for our vacation. We take a little trip on 1 day a week. We take off and we go usually to this oasis, which is about an hour and a half, 2 hours away. And at the oasis, this is actually closer to the site. Here's some horses. And here's asses. Here's some asses of asses. These are a type of deer called pequeños. Very beautiful, very shy. You can't get too close to them. Here's a rush hour in San Pedro. You see these sheep herders. Traffic has to shut down completely. This van is waiting for 10 minutes as this herd goes down the street. So in the oasis, you also see things you don't get in the South Pole, massages. You can get there. You can go swimming in a hot stream, hot springs. It's really nice to go there to relax. And you see other things there. There's a 20,000-foot volcano. Kind of in your mind, if you ever think of the word volcano, this is what you think of, this pointy cone-shaped object with 30-degree slopes to it. And this is an inactive volcano, hasn't erupted in a very long time. But actually there's a lake at the top, a crater lake, and they believe that the conditions there make it favorable for astrobiologists, people who are studying life on other planets. They like to go there and study and hike up there. And some of our students have gone up there. Hans, I don't think you went up there, did you? I don't think Hans took a field trip up there, no. So this is our plan. We're trying to build two more telescopes up there at the site. So we'd have a capability that would actually be 20 times the capability because of the improvements that we're going to make in our detectors. This combination of 3 telescopes, this is an artist conception, where I'm the artist, aka Photoshop, of what 3 telescopes would look like up there. And if we had that, we'd have the same capability as a satellite that would cost literally hundreds of times more. And we're proposing to get funding, and that brings us to our word from our sponsor. So I'd like to thank our funding agencies, the National Science Foundation, which has funded us for a long time, NASA, which funds me, and UCSD, and also especially like to thank the organizers of tonight, Nancy and Aaron, David especially, Melanie Cruz, Mark Tiemens, Mark's in the back. So it's really nice to have you guys be able to help organize this talk tonight and work with us and give us funding and provide the resources and personnel that we need in order to keep making these really exciting discoveries. So I'm always asked, well, what books do you recommend? There are 2 books that I would recommend for various levels. There's some young people in the audience. The book on the right is a book called Ice Scientist, and it's meant for people between sort of 4th grade to 9th grade, a middle school science age. It talks about my experiment. The author interviewed me for this book, which is really nice. And then there's a book called The First 3 Minutes, which describes the properties of the Big Bang as we understood them about 20 years ago, but we're really looking at not the first 3 minutes anymore, but really going down to that first nanosecond. And so these are excellent books. And I'll post some links to some articles. This is just my website, cosmology.ucsd.edu, that Hans and I run. And we'll post links to articles that have been written, and you can find some more information in the booklets that people handed out and the articles that have been written about us recently. I never recommend this book. I actually met Stephen Hawking at a talk he gave, and he revealed to me that he writes a book every time one of his kids would get old enough to go to college. Which I find, not a serendipitous fact. It's a very difficult book, even for professionals to read. It's not particularly well understood, and they say that only about 1% of the people that have bought it have gotten past the first chapter. So do not read this book. Instead, read these books. This one, if you're a kid, or if you think like a kid, and this one, not so much. So I'd like to end by thanking the UCSD Polar Bears. There's about 8 of us, my students, the graduate students, and postdocs, and Hans Parr, as I mentioned. I'd like to thank them because they're really the ones that do the hard work, that travel to these locations, that stay there for months at a time, and really are analyzing the data and making these exciting new discoveries. And it's really thanks to them and their hard work that I can be here to present this tonight. So I'll take some questions. Thank you very much for your attention, and I'm happy to take questions. Yes, over there. Who's funding the other telescope? So they're both funded by the National Science Foundation through grants. It's an American, it's a national, yeah, it's the United States National Science Foundation. And they're really, the reason that we get to claim Antarctica as the parts of Antarctica where we work as a US possession is because of the scientific research we do there. If the National Science Foundation was not doing research there, the international law says we don't have claims to occupy or to be there. So it's really thanks to that we have that ability. Yeah. Other questions? Yeah, in the back.
Any explanations offered up for the origin of the Big Bang involved in the regress analysis?
Say that one more time.
Are there any explanations offered up for the origin of the Big Bang that do not involve an infinite regress fallacy?
That don't involve. I can't hear the last part of your question. You're asking, are there any models that don't involve something that I can't understand?
The origin of the Big Bang.
Yes.
That do not involve an infinite regress fallacy.
Okay, I'm not aware of what that means, and maybe we can talk afterwards, but I've never heard infinite regress fallacy. More questions? Yes, over there.
Would you help me reconcile driest desert in the world and snowstorms?
Yeah, so that's actually a good question. So for the last 30 to 50 years, the Atacama Desert, this plateau that we observe on, has basically seen very little to almost no precipitation. There'll be a precipitation on occasion, but what defines a desert is an amount of precipitation below a given level. So although it may not rain very much in the Sahara, and it certainly doesn't snow in the Sahara, if you measure the humidity there, the humidity is higher in the Sahara Desert than the humidity in Chile, the equivalent humidity in Chile. So the amount of precipitable water vapor, if you took a cylinder and extended it into space, and you asked how much water vapor is in there, and you condensed it down to a liquid, and Chile, we could collect, right now, today we would collect 1/4 of a millimeter of water in that cylinder. In San Diego, we would collect about 20 centimeters, so a huge amount of water. And at the South Pole, we would collect about 1 millimeter. So it'd be higher absolute humidity, but it would have more stability properties. So this was actually the rainiest, wettest winter on a summer, actually, on record. There's something called the Bolivian winter, where winter weather can occur during the summertime. So yes, that was sort of a freak season. They say that, oh, part of the desert has never seen rain in 10,000 years. Well, we saw big rainstorms when we were there, especially during Hans's visit. Yeah?
I thought Brian Greene had said in his latest book that you couldn't look back to the Big Bang because there was a plasma-like fog.
Exactly. Yeah. So that's a very good question.
Particles were formed, so how far back do you have to
Yeah. Okay.
Let's say longitude.
Yeah, so I'm glad you asked. So the question is, if you have a plasma, like Brian Greene says in his book, that a plasma of electromagnetic and electromagnetic radiation don't mix. A plasma is ionized material, so it's a gas made of charges, so electrons, protons, whatever, that are not bound into an atom. So if you do that and you shine a radio wave onto it, the radio waves will get completely reflected or bounced off. And the early universe had a plasma in it, pervading the whole universe. So it's actually true. You cannot see with vision. You cannot see with light past where the CMB was produced. So that's actually a very, very good point that you're making. We can't use that. But the analogy that what I give is that imagine, earlier today there was a marine layer here. Now imagine someone lit off a firecracker above the marine layer. A big boom would go off. You couldn't see the explosion because it would get absorbed by the cloud, which is playing the role in this analogy of the plasma. But you could hear it, right? You could hear it. You might even be able to see the imprints of the sonic wave on the cloud. Maybe it would make some ripples, right? So what we're looking for, the quantum fluctuations, produce waves of gravity. So they're produced at the Big Bang, and t equals to 0. And those waves can go through anything. Gravity goes through anything. If I have a ball over here, there's a podium, and I shake this ball, if you had a very sensitive gravitometer, you could detect the gravitational fluctuations from me moving it. Gravity goes through everything. It's the weakest force, but it has the biggest influence. But that's a very important question. Yeah, in the back.
Who makes your detector drive?
Say that one more time.
Who makes
So the detectors are made by a combination of NASA JPL, for the Caltech BICEP experiment, and by UC Berkeley for the polar bear experiment. And my team here, led by my graduate student Stephanie Moorman and my postdoc Nate Stebor, are building detectors for the next generation of polar bear that I showed you with those 3 telescopes. So we have a fabrication facility like at Intel or some semiconductor fabrication where we can build those very sensitive detectors right here in-house. Yeah?
What was the name of the book by Stephen Hawking that you mentioned before?
A Brief History of Time. Yes. Yes, Professor.
You tried to find what happened the first microseconds after the Big Bang. That was the beginning of time. To your knowledge, did anybody try to find out what happened 5 minutes before?
Yeah, so that's a question that we often get. So the question is, what happened before the Big Bang?
Yes.
Really? Yeah.
What was it?
So that's a question. That's why I say oftentimes our work touches on more than just physics, more than just particle physics, astrophysics. It touches on the philosophical, the metaphysical. It touches on aspects of learning, of knowledge that we don't have access to necessarily at the time being. But perhaps by studying the initial conditions that occurred exactly when the Big Bang occurred, we could learn about, was there an essence? We basically believe that time itself what came into existence at the Big Bang. Now, people will ask often, they've heard of things called multi-universes, multiverses, where there are different aspects of the universe that we cannot communicate with, but may come into existence, go out of existence, expand forever, some might collapse forever. Those universes, we can't see them directly, but they're not forbidden. So it may be that there's a gigantic universe, a super universe called the multiverse, people presuppose, where that has been in existence for all time. Now, this is very controversial. This relates to many aspects of theoretical physics that we don't understand very well, in particular string theory. But with the conventional techniques and knowledge that we have in theoretical physics today, we believe that time came into existence at the Big Bang. So there's no way to say what happened before, because there was no before. That's when it came into existence. For religious people say that's when creation occurred. So at that point, it's impossible really to distinguish between the two. So from my perspective, when I think about that, I think about the universe, time equals 0, and I want to understand everything that happened after time equals 0. There's no way to really ask the question in my mind of what happened. Nor I could ask, what did you look like before your parents met each other? You came into existence after a certain point. So it's true, the molecules that you're composed of existed a long time earlier. But it's an important question in metaphysics, philosophy, etc. Yeah?
You said you do not recommend Stephen Hawking's book.
Yeah.
I was wondering what your opinion was on a universe.
Oh yeah, that's a very interesting book. So there's a book the gentleman's holding up called The Universe from Nothing by a friend of mine, Lawrence Krauss, who's an astrophysicist at Arizona State University. It's a new book. He just came out with it. I haven't read it. I read reviews of it. He gave a very excellent lecture here. I invited him to come to UCSD last year. I know what his basic premise is, and his basic premise is relating to the fact that we seem to live in a universe which is going to go on forever, but become increasingly boring. I'm not going to spoil the ending for you, but the dark energy that we see in the universe causing the universe to expand, to inflate, to keep expanding at an accelerating rate. And so eventually we won't be able to see other galaxies, we won't be able to see the cosmic microwave background radiation. So the universe will be very boring for cosmologists. But keep paying your taxes because it's not going to happen for 1 trillion years from now. But it is a good book. I would say from the reviews I've read, it's a good book. It's been controversial because it attempts to prove that there is no need for God. That's kind of the pun in the title, A Universe from Nothing. We don't need God. So that part I don't necessarily subscribe to. But the physics, he's a top rate astrophysicist. Yeah, so the question is, why do we have to be at the exact geographic South Pole? Well, the reason is because there's a base there. There's a facility support structure that was built there that we can live there. Now, it happens to be that at the South Pole, there's certain advantages and there's certain disadvantages from an astronomical point of view. There's a Russian base called Vostok, which is located at the magnetic pole, near the magnetic. So the magnetic pole and the geographic pole are not the same thing. The magnetic pole is where the magnet end of the Earth's magnetic axis penetrates through Antarctica. The geographic pole is the axis on which we're rotating. So there happens to be a base built there for the last 50 years that the U.S. has occupied. And it's grown to build a $200 million station, so it's pretty hard to turn that down. Otherwise, we have to bring our own stuff like we do in Chile. Yeah?
How did you know you wanted to be an astrophysicist, and what educational path did you take to become one?
Yeah, so the question is, how did I know I wanted to be an astrophysicist, and what educational path that I took? So the second question is probably easier to answer. So I have a bachelor's degree in physics, I have a PhD in physics, and then after that, after getting a PhD in physics, I specialized in doing something called a postdoc, where I was at Caltech and Stanford and created this experiment called BICEP, which then led to joining other collaborations. Science is very collaborative. It's not, the best part about it is the people that you get to work with. Like I said, I get to work with 17-year-olds and 70-year-olds, and I get to interact with the world's smartest people. So that to me is really exciting. That's kind of what inspires me to this day. As to what inspired me in the beginning, the original inspiration was when I was 10 years old. We went out with my mom to get my 10th birthday present, and she was pregnant with my youngest brother, and we were driving and we got sideswiped by a car, and then 5 hours later she delivered my youngest brother. The present that I got that day was a telescope. That was my first telescope. So I felt there was something very inextricably linked between that event and also always looking up at the stars and wondering why things were where they were. And this was 20, 30 years ago almost by now. And looking up and seeing that, hey, I'm looking out and tonight you could see a planet back then I could see a planet, let's say Jupiter, I saw Jupiter, and I remember writing down in like a diary, I saw Jupiter tonight. I looked it up. I had to wait until the Sunday New York Times came out, and they published a one little blurb thing that, oh, Jupiter's visible. So I figured out that, oh, it was Jupiter I was looking at, and that was amazing to me. It was the first time I ever saw another world and knew that I was seeing it. And there's so many resources now for young people like your son. Yeah, in the back.
Why, given how far back you're looking, why don't the stars and galaxies affect the microwave radiation that you're able to?
Yeah, so the question is, why don't the stars and the things in front of us obscure the microwave radiation? There's two reasons for it. One is that the size of our telescope's resolution, our telescopes compared to the human eye have very blurry resolution. They don't fill up much of the optics of the telescope. So in some sense, they don't contribute very much energy to the final detected signal. The second thing is that they're essentially transparent to the wavelengths that we're looking at. The microwaves go right through them. And actually, as I told you, that image that I showed you, the Hubble Deep Field that showed all these galaxies, there was way more empty space in that picture than there were galaxies. So there is galactic emission from the Milky Way galaxy that's very challenging. We can't get rid of it other than building multiple telescopes and subtracting information from one, using it to clean the other one. But for the stars and galaxies, they don't obscure things.